Hello and welcome to revision session 3 related to our applied maths unit. This presentation outlines the solutions for past paper from January 2019. Here's an overview of the paper's contents. As I recall in our revision session, we only considered questions 1 and questions 2, but this presentation does include the full work solutions for questions 3 through to question 7. And I'd encourage you to attempt all these questions at your own pace. And as with previous presentations in this lecture series, I have endeavoured to labour all the solutions to try and include all the mathematical steps required to hopefully help you understand how the solution is being developed. And here are the approximate start times related to the questions contained within this presentation, should you want to directly review a particular solution. Please note though that all times are rounded to the nearest minute. So here's question 1. I'm going to let you read all the questions and review all the solutions at your own pace. Just note this first question does relate to the formula booklet related to section 6.3 and 6.4. Here's an extract of 6.3. Essentially you will need Newton's first law of motion within the solution for question 1. And here's section 6.4 extracted from the formula sheet. And you will need the equations of motion shown here on the right hand table. Sometimes they're referred to as the Suvat equations. So I'll let you read question 1 at your own pace, given a formula in the question. And the first part of the question is to find the takeoff velocity, uppercase V here. Solution shown on the following slide. So here's question 1 continued. This is part 1, we're calculating the takeoff velocity. And review the solution at your own pace. Here's the takeoff velocity. Just now I've used the G value here for gravitational acceleration of 9.81 meters per second squared. I think generally speaking the awarding body uses 9.8 meters per second squared, or sometimes even 10 meters per second squared is stated in some of the questions. Question 1 continued. This is part 2. We have to find the time taken to reach the takeoff speed. We know this information, so we need to decide which equations to use, and this is where referring to the formula sheet will help. Some hints on the left hand side here. But the full work solution is shown on the following slide. Question 1 continued. Here's part 2, sub question A here. Calculating the time for the aircraft to reach the takeoff speed. Time shown here in seconds. And question 1 continued. This is sub question B. We've got to calculate the distance travelled in this time. Here's the equation extracted from our formula sheet. The distance travelled shown here. This is the preferred equation to use to calculate distance, but just to show it can be calculated using other equations. That's perhaps a non-preferred equation to use here, as requires transposition, but of course the answer for distance will be the same. And question 1 continued. Sub question C, we're asked to comment on the answers to parts A and B with reference to any simplifying assumptions. Comments added on the next slide. Here's question 1 continued. Sub question C. I'll let you review this slide at your own pace. And question 1 continued. Question C. Just for your reference, I've shown the formulae we used here, just included the friction force. So considering the friction force, the acceleration will be smaller. And then calculating the time, having a smaller acceleration, will give a longer time. And then calculating the distance, have a longer time, you'll have a longer distance. Question 2. Solution here relates effectively to a free body diagram of mass m. Notice in the question we're allowed to use gravitational acceleration as 10 meters per second squared, so I think they just stated that to make the numbers easier to manage. Just note that they state in the question the mass m is in equilibrium. Here's question 2, continued. We're asked to sketch a diagram of a quadrilateral showing the forces acting on mass m. They say a closed chain of 4 vectors, and that's because On the previous slide, they stated that the mass m is in equilibrium. It's not moving up or down, left or right, or rotating around a fixed point. So we're asked to indicate on a diagram, a force vector diagram, the magnitude of each of the vectors in terms of m1, m2, and the known values stated in the question. Solution shown on the following slide. It's question 2, continued, part 1. Now, this is quite a difficult question for students, I feel. You have to understand that you're considering a free body diagram of mass m. So I'm kind of like cutting mass m, if you like, out of the pulley system, and I'm just considering the forces acting on mass m. So the forces are effectively the 500 newtons acting down, the 200 newtons acting to the left, and we have this force here of 10 multiplied by m1, and this force here of 10 multiplied by m2. We don't at the moment know the values of m1 and m2. Now what we need to do here is to produce a force vector diagram. Forces are in newtons here because everything is multiplied by 10. And we know from the question the 500 newtons and the 200 newtons, that's defined. So we can start from our origin shown here on the diagram. And we can draw vertically down our 500 newtons. This could be drawn to scale. We know the 200 newtons is from right to left horizontally, so we can on the end of the 500 newtons draw 200 newtons. So that now defines point O and the end of vector 200 newtons. But we don't know the specific values of the other vectors. So what we're going to do is essentially construct a diagram by using what we term construction lines, as shown here. So we basically just using a protractor draw at the end of the 200 newtons a line in the direction of the 10m1 force. We just draw it through the point at the end of the 200 newtons force. This construction line is at 60 degrees to horizontal because that's what we're given in the question. We don't know how far to draw the line, but it's just a construction line. Then we consider our origin, and we draw a construction line, this time at 40 degrees to horizontal, shown here. And where these two lines cross, we can then sketch in the actual force vector diagram. If it was drawn to scale, of course, we could actually measure the lengths of the vectors to actually find the forces, but the question doesn't ask us to do that. For the reference, we have a separate YouTube video on this channel that outlines how to draw vector diagrams using a graphical method. That provides background information as to the solution in this case. Question 2, part 1 continued. This just shows the completed vector diagram. As I said, if it was drawn to scale, you could literally measure this line and this line to determine the values of these vectors, and so the values of m1 and m2. Question 2 continued. This is part 2. Now we have to write each of the 4 vectors in part 1 in the form of ai plus bj, where I and j are perpendicular unit vectors and a and b are expressions involving m1 and m2 and the stated values given in the question. So here we have to resolve each of the forces into the x and y components, and I'll show you my solution to this on the following slide. So question 2 continued. This is part 2. This actually slides from our lecture. I've just shown how to resolve 2 of the forces here for m2 and m1. They're resolved into their vertical and horizontal components. And again, on our YouTube channel, there is a specific lecture related to what are called concurrent forces using the analytical method of resolving forces into their x and y components. Again, that's just for background reference. What I have done slightly differently here within my solution is to consider theta positive anti-clockwise from this location here. If we apply to this convention, then it makes it quite easy to write down the equations. So this angle here is the 120 degrees in this case. Now when we consider the force associated with mass m2, the vertical force is the sine of 40 degrees, the horizontal force is the cos of 40 degrees. But when we consider the force associated with mass m1, the vertical force is associated with the sine of 120 degrees, and the horizontal force component is associated with the cos of 120 degrees. So that's the notation I'm using for the angles in this particular question. I'll show you the full work solution on the following slide. Question 2, part 2. Here's the solution for the various forces. I've labelled force F1 associated with mass M1. So here's the horizontal component, here's the vertical component. So horizontal is denoted by I, vertical component denoted by J. And I've just simplified the values here. F2 is associated with M2. Again, our values stated here. It's clear to see from the diagram that the force associated with the mass of 50 kilograms is a purely vertical force, downward force, so that's why it's negative 50 here. And the force associated with the 20 kilogram mass is purely a horizontal force, shown here, from right to left, why it's negative. And notice I'm using masses here. Question 2, solution continued. Part 3, we now have to calculate the values of M1 and M2 so that the mass M remains in static equilibrium. So the hint on this slide is to firstly consider horizontal equilibrium. You'll generate this equation, which I've labelled as 1. Then consider the vertical equilibrium. You'll generate this equation labelled as 2. So 2 equations and 2 unknowns. We can solve these simultaneous equations. I've used the method of substitution. So I substitute equation 1 into equation 2. My answers for M2 and M1 are shown here. If you think you can attempt this question without further assistance, I would encourage you to stop the presentation and do so now. But I'll show you the full work solution on the following slides. So question 2, continued, this is part 2. I'll let you review the solution at your own pace. I'm going to generate our 2 equations as shown here. Question 2, part 3, continued. Again, I'll let you review the solution at your own pace. Essentially, we calculate M2, shown here, and M1, shown here. So that's just simultaneous equations. This is the in-class solution we worked through on the board just for reference. Had very slightly different values for M2 and M1, but that's because I rounded some figures up on this particular solution. Question 2, continued, part 4 here. We inform that the vector product or cross product of 2 vectors, A and B, is a vector perpendicular to the plane containing A and B, having a magnitude, the magnitude of vector A multiplied by the magnitude of vector B, multiplied by the sine of the angle between the 2 vectors. The diagram shown at the bottom here, the angle between our vectors, shown here and here, is 80 degrees. I'll show you the full work solution on the following slide. So question 2, solution continued. I'll let you review the solution at your own pace. Just notice we're using the G value of 10 here because that's stated in the question. Here's question 3. Relates to electrical context. It involves use of complex numbers. We can see in the questions for the inductor, ZL is a complex number, and for the capacitor, ZC is also a complex number. We're informed that the total impedance is given by this expression. In other words, adding up all 3 of these separate impedances here. Question 3, continued. So part 1, given that the frequency is 50 Hz, we have to calculate the value of the angular frequency omega, shown in the equation here. To do this, we'll need to refer to the formula sheet, where you'll see that the angular frequency omega is defined as 2 pi f. So given the frequency in the question, we can calculate the omega. Solution shown on the following slide. Question 3, continued. Part 1 solution. So knowing the frequency is 50 Hz, we can calculate the omega, 100 pi radians per second, or approximately 314.2 radians per second. Question 3, part 2. Sub-question A here, we've got to express ZT in the form of A plus BJ, or JB. Here's the expression we're trying to find for ZT, and we need to use the formula given in the question here. Full work solution shown on the following slide. Question 3, part 2, item A. Here's the full work solution. Need to be careful here because we need to refer to the use of the complex conjugate shown here in the bracket. Again, we've covered this in a previous presentation related to complex numbers. I'll let you review the solution at your own pace. I've tried to labour it here. Note that of course j squared has the value of -1. Here's the value for zt. It's 20 minus j 70.1527. That would have the unit of the ohm. Question 3, part 2, sub-question B. Now we've got to represent zt on an argand diagram. This is shown on the following slide. Question 3, part 2B here. Here's the argand diagram. And we have 20 on the horizontal axis here and negative 70.15 on the vertical axis. Question 3 continued. Part 3, sub-question C. And now I've got to express zt in the form of r multiplied by the bracket cos theta plus j sin theta. Solution shown on the following slide. Question 3 continued. Part 2, sub-question C. Here's the solution. Part 2, subset D. Now zt is expressed in exponential form, which is equal to e to the j theta. Solution shown on the following slide. Question 3, continued. Part 2, sub-question D. Notice in the exponential form theta must be in radians. And I've actually shown two solutions here between 0 and 360 degrees or 0 and 2 pi radians. Here's question 4. Basically it's a geometrical and an area and volume type question. Here's part 1. Sub-question A, we've got to show this expression given the diagram in figure 3 to let you review these solutions at your own pace. Question 4, part 1. Sub-question A here is a solution. Find theta. Question 4, this is part B here. Again, another proof. You have to show that the shaded area A between the chord and the circumference of the circle is given by this expression. We did actually prove this in a previous lecture, so you may recall the solution here. So this is an extract from the formula sheet. We need to use the area of a sector, standard formula given to us. And just thetas in radians here. And we need to calculate the area of a triangle using this formula. In this case, the area of the triangle is shown here. Full work solution shown on the following slide. Question 4b. Here's our proof. Question 4, part 2. Again, we've got to prove that the area of the regular hexagon shown in figure 4 above is of this form, noting that d is the distance between the two parallel sides. Quite a difficult problem this, but I'll show you the full work solution on the following slide. Here's question 4, very detailed solution. I'll let you review this at your own pace. One thing you have to be aware of with this solution is the angle of 60 degrees shown here, and that this triangle shown here is an equilateral triangle. All sides and internal angles the same, and all lengths have the value of the radius of the circle. This solution essentially calculates the area of a circle of radius r, and then subtracts from it the area of the segments. There are 6 segments, one of which is shown here. To calculate the area of the segment, we use the formula derived in part 1 of question 4. I'll let you review the full work solution at your own pace. Here's the calculation of the radius of the circle. Here's the calculation from the area of one segment, the area of 6 of the segments. And essentially to calculate the area A shown in the figure, area shown here. Calculate the area of a circle, pi r squared, and subtract from it the area of the 6 segments. Here's the formula for area shown here we were required to prove. And for your reference, I'll show you an alternative solution on the following slide, which I derived before I saw the marking scheme, and an outline of the solution expected. So here's question 4, the alternative solution. As I say, this was compiled before the marking scheme was released, so an alternative version. I'll let you review this at your own pace. Question 4 continued, part 3 now. Given our geometry shown in the sketch, figure 5. Question 4 solution continued, part 3. So as to calculate the volume of the steel in the spanner, giving the answer to the nearest cubic millimetre. I'll show you the full work solution on the following slides. Question 4, part 3. Let you review the solution at your own pace. Here's the final volume stated. If it helps, here's a breakdown of the various sections I've used. I've basically calculated the area of a circle first of all, in here. And I subtracted from that the area of the hexagon, shown here. And I subtracted from that the area of the segment, shown here. That's how I derived the value for the area A1. Question 5, I'm given an equation that models the acceleration of a car. It's an exponential function here. Part 1, we have to write the equation, and the differential equation involving v. 5, question 1. So what they're hinting at here is to note that A, the acceleration, can actually be written as dv by dt, change of velocity with respect to time. That then makes it into a differential equation involving v. Question 5, part 2. We've got to solve the differential equation to find expression for v in terms of TAC and V0. Full solution shown on the following slide. Question 5, part 2, solution continued. So now our acceleration is replaced by the differential term dv by dt. We multiply both sides by dt, and we can integrate the left hand side with respect to v and the right hand side with respect to t. For reference, here's an extract from the formula sheet related to standard integrals. So we generate an equation for velocity as a function of t. This is the solution containing the constant of integration, k1, and imposing our initial conditions, we derive our particular solution, shown here. An alternative factorized format is shown below. I'll let you review the solution at your own pace. Question 5, part 3. We've got to find an expression for distance in terms of TAC and V0. Question 5, solution continued. This is part 3. So note here that velocity v can be stated as the differential ds by dt. So now on the left hand side we have ds by dt equals to our expression derived in part 2. Expression shown here. And again, multiplying throughout by dt, we can now integrate the left hand side with respect to s, and then the right hand side with respect to t. Here's our general solution for distance s, and here's our particular solution for distance s. Again, a factorized form is shown in the bottom line. I'll let you review the solution at your own pace. Question 5, part 4. We're given some values from which we can now calculate the time taken for the car to reach a speed of 34 meters per second squared. Solution shown on the following slide. Question 5 continues, part 4. Let you review the solution at your own pace. Question 5 continued, part 4. This is purely for reference, just an alternative solution where I've rearranged the equation algebraically first of all before I insert the values. It's just an alternative presentation really. Obviously the same final answer. Question 6, an alternating current, I amps here, being drawn by a particular electronic circuit at time t is given by. So part 1, we have to sketch a graph of I against t over the interval shown here. I'll show you my sketch on the following slide. Question 6, part 1, I've actually calculated here some values to help me sketch the graph. So various values of t used here. I'll show you the graph on the following slide. Question 6, part 1, here's the graph. I've actually used Excel for clarity here, but obviously you can just sketch the lines through the points you've calculated. Question 6, part 2, using calculus, calculate the time at which I first becomes a maximum. This is essentially a turning point problem. Solution shown on the following slide. Question 6, part 2, use the full work solution. I'll let you review at your own pace. Essentially we have to differentiate the equation and then equate to 0 to find the turning point, maximum or minimum. Actually two values calculated here. So using the first point we can calculate the time, which is our maximums here in this region. Of course we have to solve this using the product rule because we have a function of t multiplied by a function of t. And referring to the formula sheet, here's the product rule as stated. This is what we show here, of course. Question 6 continues, part 3, to calculate the minimum value of I. Solution shown on the following slide. Question 6 is the part 3 solution. This time we're using the second value, which is this time here. And referring to the sketch in part 1 above, we can see this relates to a minimum. Minimums here, this region. There's a value for I. And finally, question 7 is a thermodynamics context, relates to what's termed the Otto cycle. Question 7, solution continued. So we're given in the question the equation for the power stroke. This is curve D on the graph. And we're given the equation for the compression stroke, labelled as curve D on the graph here. Notice the values over which V is applicable, basically from 0.1 to 0.4. Part 1, we've got to calculate the value of V on the power stroke when the pressure is 2 megapascals. That essentially involves using the power stroke equation, knowing the value of P, 2 megapascals. We can solve a quadratic equation. Show you the full work solution on the following slide. Question 7, part 1. Let you review this solution at your own pace. Notice with the quadratic equation there are two solutions for V, but this is the only solution valid in this case because our answer has to be between 0.1 and 0.4. Question 7, part 2. Essentially now we have to calculate the area shown shaded in our graph. This means essentially integrating the area under this curve and taking the area under this curve from it. For reference, here's an extract from the formula sheet related to standard integrals. Full work solution shown on the following slide. Question 7, part 2. Here's the full work solution. I'll let you review this at your own pace. All standard integrals. That concludes the presentation related to the Jan 2019 paper. I must say I personally found it very difficult in places. When I first attempted the questions without the marking scheme, I did have some errors. But the object is to now help you in the development of your maths proficiency with this level of study. I wish you well in this final exam.